So our next speaker, we have Mark Krischer. So Mark has over 20 years experience across mobility and security technologies and joined Cisco in 2001 through the Radiata acquisition, where he was the director of software engineering. So as part of Cisco's wireless networking business unit, Mark led the Sydney software engineering department and was also responsible for the design and development of such technologies such as EAP Fast, which is fantastic, and protected management frames, which is really, really good work as well. So prior to his involvement in wireless, Mark focused on intrusion detection and the application of public key infrastructure, or PKI, to secure networking protocols and services at BBN Technologies. Through his engineering work, Mark holds 18 patents in wireless and security. So I think we are very, very fortunate to have someone of his experience and caliber joining us here today. And he's going to be talking through the evolution of wireless security with WPA3 and Wi-Fi 6. So I'm very, very intrigued and very interested to see this presentation myself. So I'm very, very glad I'm here. So without further ado, I'll pass it over to Mark. So Mark, if you want to share your slides there, mate. And I noticed you got a few little Cisco devices behind you. So there we go. All right, I'll kick it over to you, mate, and look forward to the presentation.
All right. Let me get this started. That's what I want. Sorry, give me a sec. Put that you over here. Come on. Sorry, I had this all rehearsed and ready to go. Here we are. All right, share screen, application. There we are. Okay. Hello and welcome, everybody. I obviously would have much preferred being up in the Gold Coast with you all, as I'm sure you guys would as well. What I'd like to do today is kind of take you through where we're at from a wireless security perspective. We'll look a little bit at what we do today, but also tie into it some of the things that we've been doing to improve wireless security, specifically around WPA3 and how that ties into Wi-Fi 6. I will try and keep an eye on the Q&A panel as I go through, but thankfully following this session is the lunch break, so I will stick around in the room as well if there's questions in the Q&A after that. So let's get things started and kick things off. So I like to kind of set the stage and think about what is the wireless attack surface? What are we actually trying to protect against? So the big issue that we have with wireless networking is recognize the wireless network propagates beyond the traditional physical boundaries of the wired network, right? We have the luxury of physical security to protect my wired network, those Ethernet ports, but from a wireless perspective, attacks can come from anywhere within the bounds of that RF domain. And so I'm worried about things like passive scanning attacks, active spoofing attacks, and active jamming attacks. So that's on the RF side, people trying to attack layer 1 of my network. So the wireless threats then that I'm looking at, we typically focus on rogue APs as the sources of these different vulnerabilities. We talk about honeypot APs and evil twin attacks, but we're also worried that someone's going to take an access point, put it in our physical network to provide unsecured backdoor access. And then the clients themselves can introduce vulnerabilities. They might be bridging the wired and the wireless networks. My users might connect to unsecured wireless hotspots where they might get exposed to vulnerabilities, which then they bring back into my network. And then we worry about data seepage, which is the clients just leaking information based on how the protocols themselves work. So kind of looking at where we would start here, right? Let's get some fundamentals on 802.11. Everything begins with a beacon. So the access points are going to send out a beacon for every SSID that they support. And that's sort of advertising what they have available. So if we had been up on the Gold Coast for this event, we'd all be looking to join the Wi-Fi for the event. Maybe we'd find an SSID for AusCERT 2020, and we wouldn't necessarily have any support or credentials, so maybe the security would be open. Of course, this is AusCERT, so we probably want to, you know, at least use a pre-shared key and some passphrase, which we'd have to advertise and somehow make available to everybody, because that's going to be really secure to put signs up everywhere. On the enterprise side, we would use WPA Enterprise. And so again, I'd have my different SSID. We do talk about the idea of hidden SSIDs, but recognize that's, you know, really security through obscurity. All we're trying to do is prevent the SSID from coming up when you use your device. But anyone listening is going to see those SSIDs, because at the same time, clients are looking for networks to join, and they're going to send a probe request for every SSID that they have joined. And the idea is that APs that support that will respond. So even if the AP hadn't sent the SSID in a beacon, it will still reply with a probe response, so we can see what SSIDs are available. I talked about data seepage at the start, just as an example of this. You know, my device is going to send probes for everything that's connected to ever. So, you know, if you look at the probe request coming out of my device, you'll know that back before COVID, I spent a lot of time in the Qantas lounge and at various hotel chains. Now, what we next need to happen is I've got to decide what to join. And the important thing to recognize here is it's the client that makes the decision as to which AP it's going to join. Now, my examples, I'm going to use a controller-based architecture, but recognize the same principles would apply from a cloud-based approach as well. And so the access point sends an association request for a specific ID to join. We get the response. The network might also send a disassociation request to a client, basically saying, would you please leave our network now? The interesting thing about that management frame is it's bidirectional. A client can send a disassociation request to the network. You might say, well, why would I need to do that? Well, that's for a roaming event. I will disassociate from one and do a reassociation to the AP that I'm joining next. So let's talk a little bit about the security framework that we have. So we talk about wireless protected access, WPA. What is this? So we have the IEEE 802.11 standards. 802.11i is the wireless security standard. The Wi-Fi Alliance is an industry standards body that creates interoperability standards. So the original WPA was based on the draft standard for 11i, so we could get it out the door quickly. And then with the final version of 11i, we had WPA2. You'll note the different TKIP and AES encryption. Around the same time 11i was being developed, that is when NIST was selecting the advanced encryption standard as well, deciding ultimately on the Reindahl algorithm. And so we were waiting, one, for that to be finalized, and two, we then needed all the Wi-Fi chip manufacturers to implement AES in hardware. So from an authentication perspective, we talked about the two methods: personal, which is pretty much for the home network, based on a pre-shared key, and WPA Enterprise, which is based on 802.1x. Now, where we're at is the Wi-Fi Alliance has introduced WPA3. This came out last year, and you know, WPA2 finalized in 2004. So that's over 15 years we were using that, and so it was really about time that we refreshed the standard. And we'll talk a little bit about what's come in with that. So the first piece, which in some ways I find to be the most important, the Wi-Fi Alliance really upped its game and took security to another level across the board when they decided that WPA3 was going to be mandatory as part of Wi-Fi 6 certification. As you'll see when we go through the advances that WPA3 brings, what we basically did was raise the bar for wireless security for all Wi-Fi 6 networks. And as of July of this year, the Wi-Fi Alliance took that one step further by making it mandatory for all WFA certifications. So even if I come out with a brand new device that doesn't support Wi-Fi 6, it's legacy Wi-Fi 5 or 802.11ac, that must still get WPA3 certification. Now, to some extent, one of the more interesting things is not what we've added to WPA3, but what we've taken away. And so we've used this as an opportunity to deprecate and remove all the old legacy protocols that honestly should have been dead and buried years ago, like WEP, TKIP, SHA-1. As late as last year, I still had customers saying they had legacy devices that needed WEP and that they needed WEP support. Well, that now is off the table. We really need to refresh those legacy devices because they are introducing vulnerabilities into our network. Now, when we talk about the Wi-Fi Alliance as an industry standards body creating interoperability standards and interoperability tests, one of the interesting things is predominantly they've been focused on just do things talk to each other. With the introduction of WPA3, though, we've started negative testing, really looking to see, are these devices doing bad things? Do they have vulnerabilities that expose the network? And so that's this idea of negative testing. Now, a couple mandatory features. Two of the key ones that we'll talk about: protect management frames, 802.11w, as well as a replacement for WPA PSK, which is simultaneous authentication of equals. We'll talk a little bit about the crack attack that came up a couple of years ago, and that's an example of where we're now going to do this negative testing. We do explicit testing for the crack vulnerabilities. Some optional features: Suite B crypto, which is really looking at resistance to quantum computing from an encryption perspective. And then there's two optional certifications, which are not necessarily part of WPA3, but separate certifications on their own. That's Wi-Fi Certified Enhanced Open, which is looking at what we can do in the public Wi-Fi space, and Wi-Fi Certified Easy Connect, which is looking at the IoT space. All of those in blue we'll talk about as we go through here. All right, so let's get back to our client that's trying to connect to the network. We've done the association. Now we need to authenticate into the network. So I'm going to need to introduce now a AAA server to provide that authorization. A little bit of nomenclature. The client plays the role of the supplicant. The wireless network infrastructure, that's going to be the authenticator. And the authentication server, the AAA server, that's what's going to actually do the authentication sequence. Obviously, I need my credentials somewhere, so I will have a credential server. Typically, we see something like Active Directory for that. So the important thing to recognize here is 802.1x is between the supplicant and the authenticator. The actual authentication sequence, our EAP type, that is between the supplicant and the authenticator. And so I do my association, I come back with my identity. We're going to use that to do some negotiation on what EAP type we're going to use. And again, that auth sequence between the supplicant and the auth server, which means the authentication server needs to send the EAP success message to the authenticator to say, yep, Mark Krischer is who he says he is. You can let him on the network. So let's talk briefly about these EAP types. Two that we see most often, you've got Microsoft PEEP, you've got EAP Fast, which was developed by Cisco. These are tunnel-based methods. So that's the outer method. Then we've got a couple different ones that we use for the inner method. Most common is going to be MSCHAP v2. This is your standard username password. Now you might ask the question, well, why am I doing that in an inner method? Why isn't that just the EAP type I use? MSCHAP v2 has been around for a while. It's pretty old. As you can see, it's based on DES, not even AES. And there was a nice little vulnerability built into the protocol. As you can see, we got to pad out the last block there, which opens us up to a known plain text attack. The point is that vulnerability is only exposed if we are able to see the exchange, because we're doing this over the air and an attacker can passively be listening. That's why we need to do it as this tunnel-based approach, so no one can sniff that exchange. Some other methods we use, generic token card, or we can use certificates with ETLS. Of course, if I'm using certificates, I don't need to do it in a tunnel. I could just use that directly. So as a result of this auth sequence, I end up with a 256-bit random string, which I'm going to use as my keying material. This is the pairwise master key. Again, the authenticator wasn't part of this, so my auth server will pass that PMK to the authenticator. We can now start the encryption sequence. The authenticator is going to create another random value called the anonce, which it will send to the supplicant. And we can now create a session key, the pairwise transient key. It is based on this 5-tuple, the PMK, the anonce that it just received, an S-nonce that the supplicant will create, and the 2 MAC addresses. So the supplicant creates the pairwise transient key. We need to send the S-nonce back to the authenticator so it can create the PTK. And we're going to send a message integrity check. This allows the authenticator to verify that it created the right PTK. We also need a key that we're going to use for multicast and broadcast. That's the group transient key. So we'll send back the anonce, but this time with the message integrity check. This allows the supplicant to validate that, yes, we all have the right PTK. We'll send the GTK encrypted with the PTK, a sequence number. The supplicant says, yep, it all looks good, and we'll send an acknowledgement. This is the 4-way handshake. And so we're, about 15 minutes in, and we finally have an encrypted link. Congratulations, everyone. So this is getting us set up for how I can now do my encryption. That's the authentication piece. But we need to look at this separately to authorization, right? So authentication is, can I get on the network? Now, what am I allowed to do once I'm on the network? While normally we would view authorization as a broader network security perspective, there are some implications for wireless network design that I want to highlight. One of the simplest approaches we use is static VLAN assignment. So the idea here is I have a VLAN statically assigned to a given SSID. So the simple example I would use, university network, I've got a staff and a student VLAN. I will create a staff and a student SSID, and I join whichever one to get access to the network and be on the correct VLAN. The problem with this is I need an SSID for every VLAN that I want to implement. Remember what we said at the start, right? For every SSID, I need to send a beacon. Beacons are sent at the lowest transmit mandatory data rate. The implication here is if I have a lot of SSIDs, because I have a lot of VLANs, my AP will spend all of its time sending beacons and very little time actually passing some useful traffic. So the idea is I want to minimize the number of SSIDs that I have. So instead of static VLAN assignment, we look at dynamic VLAN assignment. So using that same example, the idea is I join a common SSID for the university. Based on my identity, that will be tied to, for example, an Active Directory group that identifies me as staff or student, and that puts me now on the correct VLAN. But we're actually moving beyond that sort of approach, and we're now starting to see some momentum behind scalable group tags. Scalable group tags basically moves away from an IP source and destination address. And the reason why this is relevant in the wireless space is I'm mobile, I'm moving around, I could connect into the network from multiple places that might be actually on different network segments. I'm using DHCP, I'll be getting different IP addresses all the time. And so what that leads to is an exponential growth of my access control list. So scalable group tags, by its very name, allows us to be a bit more manageable in terms of the number of ACLs that I need. All right, so I've connected to the network, I've authenticated, I've got an encrypted link, I'm authorized for where I'm going to connect to, and now I'm actually starting to walk around, I'm roaming. And so I've got to go through the whole sequence again. If I'm doing something like real-time voice and video, that's going to introduce delay, my calls could drop. And so we're looking at how can I improve the performance of my roaming. There's really two problems that I'm looking to solve here. The first is on the client side. I've got to go and scan all the available channels across 2.4 and 5 gig, and then pick an AP to join. The other problem is that whole sequence of the authentication and the four-way handshake. So 3 protocols actually come together to address secure fast roaming. This is 11K, V, and R. The Wi-Fi lines kind of wrap them up, what they call Wi-Fi Agile Multiband, and this is actually a mandatory requirement of Wi-Fi 6. So the idea here is to address the first problem of channel scanning and AP selection. We've got 2 protocols, 802.11k, which is neighborless. So the wireless infrastructure, the APs actually know who their neighbors are. And I don't mean from a physical deployment perspective, I mean in an RF perspective. What APs can I hear in my environment? And so I will pass that information to the client, so you don't have to scan every channel. Here are the APs that are in your environment. Here's the channels they are. Gives you a much smaller subset of channels to scan for your AP selection. We can also get a bit more prescriptive. While we said that the client decides what AP to join, 802.11v allows the AP to say, hey, I want you to go and join this access point. To address the re-authentication, the rekeying, we have 802.11r. What this is basically saying is I've already authenticated to the network infrastructure. So when I move to a new access point, I'm really just saying, hey, I'm still Mark Krischer, let me on the network. Let's just get a new session key started. There's 2 different ways that this is implemented. And so you may see it referred to as over the DS. What's that? Over the DS is the distribution system. The idea here is once I decide which AP to join, I actually get my AP to communicate over the network to the new AP to negotiate on my behalf. So once everything's set up, the new keys are sorted, I can then just go and do my roam. Now, of course, this is going to add a little bit of additional delay. And so what we typically recommend is the second method, which is over the air. And so here, I'm actually going to go off channel, connect to the new AP, get things set up there, go back to my original AP to disassociate, get any packets that were queued up for me, and then proceed. Over the DS, a bit more reliable, but again, can introduce the delay. So again, over the air is the default recommendation. Again, what I said, the whole purpose of this is to keep the roaming times down. As you can see here, taking these 3 protocols into account plus quality of service really serve to do that. The magic number, 100 milliseconds. If I stay below that line, that means I'm not going to impact any real-time voice and video traffic. Now, one of the things that came up as we started going down the path, particularly with 11R, was there were some vulnerabilities discovered. This was the crack attack from a number of years ago. It was actually a collection of 10 different vulnerabilities, and what they ultimately ended up causing was that keys could be reused, which would, of course, set me up for a known plain text attack. One of the 10, that was actually specific to the infrastructure. The rest were all client-based. And the one for the APs, that was specific to 11R, which is why I bring it up in the context of fast roaming. Important to recognize, this was actually an industry-wide issue. And what I found really impressive from an industry perspective was how quickly everybody kind of geared up to work to mitigate the issue across the board, both on the infrastructure and the client side. So real impressive to see, the effort that went in to make sure that this didn't create challenges and vulnerabilities for wireless networks. As I said, the flaw basically forces allows you to reuse the key stream, which creates this vulnerability, and it would be done by a rogue AP, effectively doing a man-in-the-middle attack. And so typically rogue AP detection was what we used to mitigate it until the vulnerability was fixed. And as noted before, certification for WPA3 introduces crack exploit testing. Now, more recently, there was another vulnerability discovered, the crook vulnerability. This was actually the result of a bug in some of the wireless chipsets. The result of this was the passive scanning attacker would actually be able to decrypt the Wi-Fi frames without knowing the pairwise transient key. In hindsight, the bug is actually kind of funny. So I disassociate from the network. And so the chip says, okay, the client is not on the network anymore. I don't need the pairwise transient key anymore. Therefore, I will zero out the register that was storing the key. Only the chip then goes, ooh, I still have some packets that I need to send out. So I better send those quickly now. Only we just zeroed out the key. So those packets get sent with a pairwise transient key of all zeros, which is why the attacker is able to decrypt those packets. As I said, it's kind of funny unless you're actually on the downside of the attack. Now, it does kind of beg the question, right? Because the way that I'm going to expose that vulnerability is I'm going to send a disassociation request that's going to force the whole chain of events. So why are these devices listening to these spoofed management frames? Well, the answer is that there was no way to verify the integrity of management frames to know that they were coming from the legitimate client or AP or an attacker. And so that is the problem that 11W aimed to solve. It basically allowed us to add a integrity check across both unicast and multicast, and in fact, add encryption or confidentiality onto the unicast management frames. As I said, this is now mandatory for WPA3 and Wi-Fi 6. And the reason this is so important is if we look at the vast majority of wireless attacks that we see today, they typically start with a spoof management frame, typically a spoof disassociation or deauth request. And so this effectively immunizes us from the vast majority of attacks that we see on the network today. Now, that was all kind of focused on the infrastructure side. Let me shift gears a little, and look not at enterprise, but now start to look at things in the consumer space or even what we use, for guest type access. So this is WPA personal. And of course, with a home network, we don't have all the infrastructure in place. We don't have a AAA server. Well, I guess this is an AusCERT talk, so maybe some of you actually are running a AAA server at home, but in general, we don't have AAA servers at home. And so that means there's no auth sequence, which means there's no pairwise master key. So instead, we have the passphrase, which is used to generate the pre-shared key. Now we're going to do the four-way handshake just like we did before. But this time I want you to actually take a look at what's in that 5-tuple. So instead of the PMK, we're going to use the PSK, and then we've got the 2 nonce values and the 2 MAC addresses. Well, out of those 5, only 1 is actually a secret. The nonce and the MAC addresses, those are sent over the air in the clear. So the entire security of the generation of the pairwise transient key is based on the security of the PMK or the pre-shared key. So the PMK is this random 256-bit string. So, that's actually not too bad. But the pre-shared key depends on the passphrase. If my passphrase is AusCERT 2020, basically we're opening the door for offline attacks. And I certainly don't have to tell this audience strong passwords matter. But this is actually why from a WPA PSK perspective. So to solve this vulnerability, in WPA3, we're going to use a new protocol called Simultaneous Authentication of Equals, or SAE. It is based on the Dragonfly key exchange. And the real important thing to take away from how the Dragonfly key exchange works is the security is not tied to the complexity of the shared secret. So that eliminates that offline dictionary attack vulnerability. The result is going to be a 256-bit PMK. I do my my 4-way handshake as normal. and I support 802.11w. Now, on the downside, recognize there's going to be, a bit of legacy that we're going to be dealing with for quite some time. So we do introduce a transition mode supporting both WPA2 PSK and WPA3 SAE at the same time. Of course, that opens up the door for downgraded attacks. And in fact, there was some work done on the Dragonfly handshake, and there was a series of attacks identified that were coupled together under the name Dragon Blood. One of the key ones being this backwards compatibility attack that we can trick clients into connecting using WPA2 personal, which again exposes weak passphrases. There's also some vulnerabilities that we need to be aware of on the infrastructure side. And there we're looking at using anti-exhaustion mechanisms and also the capability to blacklist misbehaving clients to prevent that from impacting things on the infrastructure side. But the end result of this is, as you start migrating WPA3, you do just want to check with vendors, both infrastructure and clients, what they do to mitigate some of these attacks. And we would expect to see these being built into the negative testing that we do in the Wi-Fi Alliance. So that's where I'm going to use passphrase. But now let's think about the guest access perspective, where I'm just doing open SSID. So in this open environment, I'm still going to have my AAA infrastructure, but there's no real authentication happening at layer 2. There's no 802.1x. And so the idea is any packet that gets sent is going to trigger a radius event, and that's going to result in a redirect ACL. And the idea behind this is, now if I see an HTTP packet, I will redirect that to my web server to do a web authentication sequence. And then as a result of this, I'm going to capture that MAC address in the AAA, and I'm going to send a change of authorization request. So now when I come in again with a new packet, because we did the reauthorization request, I now trigger again the radius access. This time I'm going to see the MAC address, MAC off bypass kicks in, and I'm going to allow that device onto the network. Of course, we know it's very trivial to spoof a MAC address, and so we have to recognize what the limitations from a security perspective that does on the access side. But the other piece, again, there was no .1x, which means there's no pairwise master key, which means there's no encryption across that link. Now, sometimes we use MAC off bypass generically, less so from a normal client perspective, but in the IoT space. If I've got legacy devices that don't really support modern capabilities, I'll be using MAC off bypass to secure it. Even if those old devices I mentioned before that only support WEP, will probably use a combination of WEP and MAC off bypass for that. But at the end of the day, again, very, very insecure. And so what I typically recommend is those devices should be going on a dedicated VLAN, and we're locking down that VLAN so the devices can only talk to the very specific applications that they require. Of course, things are about to get a little bit more complicated when it comes to using the MAC address for any sort of policy. iOS 14 dropped just yesterday, and along with Android 10 and Windows 10, we're now starting to see what we call a private address. This is a random MAC address. Now, random MAC addresses are not new, right? We've actually been seeing them for a bit. And they were initially put in place to mask my identity and prevent things like location analytics. What's new now with this private address approach is I'm going to use that random MAC address even when I am associated. Now, things aren't completely horrible in the sense that what iOS, Android, and Windows are doing is I will use the same MAC address consistently every time I join the SSID. So it'll be different for each SSID, but it's not like I'm going to change every time I join the network subsequently. So, it does give that privacy perspective. but it is going to create implications beyond just location analytics. Anything that you're using MAC address from a security perspective, is something that you're going to now need to take into consideration. So on the guest access piece, there's two other things that I want to look at. First is what I talked about before, Wi-Fi certified enhanced open, which is a optional certification associated with WPA3. The problem it's trying to solve is the fact that I don't create a PMK. I don't have any encryption of that link. And so we use what's called opportunistic wireless encryption using Diffie-Hellman to do a key exchange, so I can at least do a encryption on that open SSID. The problem is Diffie-Hellman is susceptible to a man-in-the-middle attack. So the idea is I'd show up, say, at the airport. I think I'm connecting to airport Wi-Fi, but instead I'm talking to the rogue access point. I have an encrypted link to the rogue. It sets up a link to the legitimate access point, again encrypted, but the attacker now has visibility of all my traffic. The attacker would have visibility in a purely open network, so it's kind of a trade-up. And with COVID, none of us are going to airports anymore anyway. But it is something to look at, try to improve it. We've taken that one step further with open roaming. So open roaming was developed at Cisco, built on 802.11u and the Wi-Fi Alliance Passpoint protocol. And we've subsequently given control of it over to the Wireless Broadband Alliance. Put simply, we're looking to kind of decouple the access provider from the identity provider. So going back to that airport example, while I might not have an account with the airport, I do have relationships with airlines through my frequent flyers. So the airport could offer Wi-Fi, leveraging my frequent flyer credentials as the way to authenticate me onto the network. The advantage here is that we can actually do a proper EAP exchange, which means that I've got, effectively WPA enterprise level security. We actually simplify the onboarding process as well as part of open roaming. And so the WBA is really driving this forward at the moment. And in fact, they view it not just from a pure Wi-Fi access perspective, but they're looking at it as how we can bridge the gap between Wi-Fi 6 and 5G networks. Now, on the IoT side, the problem that I'm trying to solve is I've got these IoT devices, and some of them don't even have a user interface for me to configure them to get onto the network. So how can I make this work more securely than just doing something like MAC auth bypass? So the device provisioning protocol has three different stages. And the first is the bootstrapping. I'll use something like a QR code, NFC, or Bluetooth to get a public key off the device. Then I can use that public key to create a secure tunnel to do my credential exchange. And now I've got a pairwise master key. I do my four-way handshake. I get to take advantage of 11W exactly as we've seen before. Now, all of that is really network infrastructure focused. The last thing that I just want to touch on briefly is the attacker piece, the rogue access point. So we define a rogue AP as any access point that's not part of our infrastructure. Now, if you think about it, by that definition, most of these rogue APs are actually going to be legitimate. And what I need to do is understand which ones are malicious. Correctly differentiating them is going to be really important in terms of what I do to secure my network. I said at the start, we're worried about rogue APs introduced onto my physical network. Detecting that is really hard because when I see a rogue AP, I'm looking at the wireless interface, the wireless MAC address. But on the wired side, when I'm looking for it, looking in the CAM tables of my switch, I'm seeing the wired Ethernet MAC. Now, most devices, they allocate those MAC addresses sequentially. So I can, find the correlation and try to identify that. But if I'm a malicious attacker, I'm going to pick completely different random MAC addresses that are unrelated. So you're not going to be able to identify me in that way. So at the end of the day, wired 802.1x really matters. Now, the other side of this is the rogue client. Rogue client is any client which is connected to a rogue AP. What I care about are my clients that might be connected to a malicious rogue. Because remember, my client could be connected to the coffee shop downstairs, which is legitimate. The other thing, clients can create ad hoc networks. So that looks a little bit different to a normal client and AP-based network. But if I am wired into the physical network and having an ad hoc network, does that create a backdoor for me? Question, let me just take a quick look. If an AP returns the client with a list of other nearby Wi-Fi networks, could that be spoofed by an attacker to trick a user onto an illegitimate network? 100%. That is exactly what we're looking at. As a malicious rogue, I will send a disassociation request to my legitimate client to force it to go off the network and roam. This rogue AP, I'm going to use the same SSID. So what I'm trying to cause is to knock the client off the legitimate network and have it roam to my illegitimate network, as you put it in that question. So how do I mitigate against that? Well, this is where rogue AP containment comes into play. I'm going to try to contain the rogue, and I'm going to attack the attacker. I'm going to send a spoofed disassociation request to the client, the rogue client connected to that rogue AP. So just in the same way that the rogue knocked me off, my legitimate network, I roam to it, my legitimate network's going to knock me off to go back. If I do this, I do need to, again, make sure that it really is a malicious rogue. The coffee shop downstairs doesn't like it when I attack their network. Marriott actually got into trouble. They wanted people not to use their 4G hotspots, but to pay for hotel Wi-Fi. And they actually got fined by the FCC for using rogue containment to force people onto the hotel Wi-Fi. But remember what we talked about, protected management frames, right? Rogue AP containment is going away in a WPA3 world. So we're going to need to think about the implications there. We're going to be much more focused on detection. And I'm going to have to maybe rely on wireless location technologies to physically locate rogues, and I'm going to need to physically mitigate them as opposed to using rogue AP containment. Question on multi-factor authentication over .1x. So while multi-factor is all the rage at the moment, and certainly we use it ourselves with Duo. We don't see that it's useful for the access to the wireless network, because if you think about what we do from the roaming perspective, just adding that extra bit of complexity actually inhibits what we're trying to do. So instead, it's about doing the standard EAP types that we talked about, and then I would use Duo or whatever multi-factor authentication for the applications that I'm connected to. So we use MFA for the application security as opposed to the network access. When I use MFA for remote access, that's a little different for my VPN because I'm stationary. It's really the mobile aspect to wireless, which is why we typically don't use it on the wireless network. I will try to get to, there's some other questions I'll answer after I finish, but I do recognize I'm over time. So I just want to thank you all for your time. And just remember, the wireless network is just one link. It's one piece of the puzzle. So it's got to be just one part of your overall network security strategy. Thank you very much.
Cool. Thank you very much, Mark. So I'll probably need to change my password now, or not. So we have maybe 1 or 2 minutes for a few questions.
Oh,
one
excellent.
thing I did want to. The one thing I did want to go through was you mentioned in the open roaming that we're using some kind of federation or identity especially in an airport example, which is a great solution. What's the potential for things like information leakage as part of that? Is there any protections in place for someone creating their own federation server or something like that, and maybe leaking frequent flyer numbers or passport details, as we've seen recently in the news with Tony Abbott?
No, that's a great question. And while we're decoupling the access provider from the identity provider, the access provider does have complete control over which identity providers it will allow. So the WBA, the role that they're taking is they're acting as that federation entity for all the different identity providers. But as the access provider, I can say, hey, I'm not letting, everybody on. So to use the frequent flyer example, I'm only going to allow federation of, the airlines that actually fly into this airport, and other things like maybe EduRoam, who could be another identity provider. I'm not going to allow that or anything else. So that the security is on how I implement it as an access provider, which identity providers I want to allow.
Right, fantastic. And there was one more question in the Q&A. If you can do it in Rogue AP, what is preventing a Rogue AP to do it to you? If you can do it to a Rogue AP.
Yeah. I think that was doing the disassociation request, and that's 100%. That's the problem that we were solving with 11W. So now the Rogue AP is not going to be able to knock my clients off the network. Remember that the client may still just roam and may still roam to that rogue, but it's not going to be able to try and force it by sending the spoof disassociation request.
Fantastic. And there were a few more questions that were kind of hovering around, but I'm conscious of time. So with that, I'm going to thank you very much for that presentation, because that was probably one of the most in-depth and technically complete presentations of WPA3 I've seen, because the information's all over the place, right? So thank you very much for that.
Thank you.